Hello, ladies and gentlemen, and welcome to my first lecture regarding advanced classical mechanics. We're gonna we're gonna deal today with a simple introduction of Lagrangian mechanics. What's Lagrange and how to deal with a system in motion in specific coordinates and how to apply Lagrangian mechanics to such systems. Today, we're gonna solve a very simple application and we'll solve more difficult and advanced questions in the coming lectures. So please stay tuned. I am Muhammad Jafar Sharafuddin. Let's start. First of all, what's Lagrange? Lagrange is symbolized by the capital letter L, and it's equal simply to the difference between kinetic and potential energies. Yes, in some books, you may find that the kinetic energy is symbolized by the capital letter T, and the potential energy is symbolized by the capital letter V, and it's okay. Don't care about that. The equations of motion for a moving system can be determined using the Euler-Lagrange equation, which is the total derivative with respect to time of the partial derivative with respect to q dot for the Lagrange minus the partial derivative of Lagrange with respect to the position equals to 0. Q refers to the position of the moving body. Q dot refers to the velocity of the moving body in generalized coordinates. But what is generalized coordinate? Simply, we can say that if we have a ball bouncing in y direction, then we can call y the generalized coordinate, where y is the position and y dot is the velocity. Let's take a simple example. If we have a ball bouncing downward with no external forces other than the weight, then the ball is moving due to a free fall motion. So the mechanical energy is conserved at any time t. And the kinetic energy can be possibly equal to half my dot squared. The potential energy at any time is equal to mgy. By substituting in the Lagrange equation, which is the difference between the kinetic and the potential energy, we get half my dot squared minus mgy. And the last step is to apply the Euler-Lagrange equation. For that, we must calculate the expression of each term in the above equation. I should derive L with respect to y dot, then the answer with respect to time. After that, I must derive L with respect to y. Then substitute each term in its convenient place in Euler-Lagrange equation. First of all, del L by del y dot equals the del by del y dot of half my dot squared minus mgy equals my dot. Deriving the answer with respect to time, we get my double dot. Now the partial derivative of Lagrange with respect to y is minus mg. By substituting the needed expressions in Euler-Lagrange, we will get my double dot plus mg equals to 0, which proves that y squared y double dot equals the acceleration equals minus g equals minus 9.8 meter per second squared. So Lagrange is a genius way to solve mechanics. It's used to solve very complicated questions, which we will deal with during the coming videos. To that time, please stay tuned. Goodbye.